Very good morning to one and all. I, Professor Ganesh Pai, Department of Computer Science and Engineering, welcome you all to the fourth day of online short-term training program on machine learning for societal applications. We are honored and privileged to have a most eminent and distinguished speaker in the morning session of fourth day, Dr. D.S. Guru, Professor at Department of Studies in Computer Science, University of Mysore. Now I request Dr. Sharmila Kumari to introduce the speaker, Dr. D.S. Guru, to our participants. Over to you, ma'am.
Respected sir, firstly I would like to mention that it is an honor for us for having accepted our invitation to deliver a talk on feature selection approaches in this training program. Dear participants, wishing a very pleasant morning. At the outset, I would like to mention that we have with us one of the eminent academicians and a researcher, Professor D.S. Guru, known as Guru in the research community. Dr. D.S. Guru is a professor in the Department of Computer Science, University of Mysore, and currently on sabbatical and associated with Naimo Technologies Private Limited, Bangalore, as a senior research scientist. He has formerly worked as the Chairman, Admission Reformation Committee, Chairman, Department of Studies in Computer Science, Director of Distance Education, Director, Internal Quality Assurance Cell, Chairman, Board of Studies in Computer Science at University of Mysore, Manasa Gangotri, Mysore. Professor Guru has obtained his PhD from University of Mysore and carried out his postdoctoral work at Patent Recognition and Image Processing Lab, Michigan State University, USA. He is a Fellow of Boys Cast, Department of Science and Technology, Government of India for the year 2005. It's the award for Young Scientist from Government of India. He is a recipient of first ARP award under Engineering Sciences, Vision Group of Science and Technology, Department of Science and Technology, Government of Karnataka, India for the year 2010. Recognized as Best Ethical Teacher at Higher Education by Rotary Mysore for the year 2011. Best Student Paper Presentation Prize in 1992 during Master's Study from Computer Society of India, Bangalore chapter. Professor Guru successfully guided 19 students for their PhD degree and currently supervising 6 PhD students. Published 80 plus research papers in reputed journals and 280 plus conference papers, and right now having H index 25 with 2036 number of citations. He is a member of advisory boards and program committees of ICDAR 2017, ICDAL 2018, ICCR 2005, 2008, 2011, 2016, ICMCCA 2011, and many more artificial intelligence related conferences. He is the associated editor for the Journal of Patent Recognition, Elsewhere Science, and have been reviewer for many journals, IEEE Transactions, Elsewhere and Springer. Professor Guru edited several books including Medical Imaging, Artificial Intelligence, Image Recognition and Machine Learning Techniques, Data Analytics and Learning, Multimedia Processing, Communication and Computing Applications, Signal and Image Processing. He authored textbooks on problem solving with C, object-oriented programming with Java, object-oriented programming with C++. Professor Guru edited journals, namely International Journal of Machine Intelligence. He is professionally recognized very well and nominated by MHRD, Government of India, as a member of Board of Management, Institute of Medical Sciences, deemed to be University Maharashtra, and invited to deliver keynote talks, seminars and speech at many international conferences, seminars and workshops, including human resource development centers in India and abroad. His entrepreneurship are many, which include Founders Trustee of Maharaja Education Trust, registered, Mysore, established various institutions in and around Mysore, including engineering colleges, MIT Mysore, and MIT Tandavpura and providing social services in villages. He is the founder president of Seva Samiti in his village, organizing several personality development programs for school children and medical checkup camps for villagers and actively involved in cultural development programs. I wholeheartedly welcome Professor Guru and request him to enlighten us with his lecture. Over to you, sir.
Thank you, Madam Sharmila. Thanks to Ganesh, sir. Good morning to one and all. Topic of my discussion today is on feature selection approaches. Of course, don't expect me to take into the more mathematical details associated with these feature selection approaches, but however, to touch upon the basics of feature selection, why, how, what are all the different classes of feature selection approaches available in literature, and in what way you being a researcher can think of extending these basic fundamental approaches to suit your specific domain and application in IBLM. So it's like going for a small walk inside a garden, getting familiar with various kinds of flowers, time being available in the garden, because tomorrow the plantation of new flower species may change a look of the garden in a different style. But still, what is the basic skeleton of the garden? What is the overall plans in the garden? So the garden that I'm talking about is what is called feature selection approaches. Probably for the last 3 days, having attended this FTP, you must have understood the things, especially on various stages of machine learning. And indeed, yesterday, Dr. Shekhar had made my job of introducing you the strong background of feature selection approaches simple by highlighting the advantages of dimensionality reduction techniques while talking about principal component analysis. So as these coordinators introduced me to you, I am from basically University of Mysore, but currently working for my research activities towards industrialization, towards productization of my research thoughts in association with one of the computer vision industries called Nanotechnology Bangalore. So probably in my lecture, I may also quote a couple of examples or the applications that we have been exploring in the industries, and also highlight what are the interesting, challenging issues that you can take up as your research topic to further explore. So before I begin explaining you the approaches of feature selection, let me just recollect the things which perhaps you must have discussed in the last 3 days. Any pattern recognition or machine learning approach involves basically 2 steps, majorly 2 phases. One is training phase, the other one is recognition, you can call it as, labeling, you can call it as, relabeling, you can call it as, classification, you can call it as, right? So in the training process, the interest lies in giving a computing technology a rich knowledge base on the population of my interest, on the samples of my interest. So during this training phase, what do? We just get a couple of samples of our interest. Probably the samples could be the samples related to face recognition. Then we collect sufficient number of samples of face images of variety of people, different people of our interest in different poses, in under different lighting conditions, right, and so on. So when we collect such samples, then we just give them for some pre-processing. During pre-processing, we just try to eliminate some noise present in them, some unwanted things, and or indirectly what Dr. Nagendra Swami said yesterday, that data cleaning or data preparation. We do a kind of data preparation during pre-processing, and then we subject it for a kind of feature extraction. Feature extraction is a method of transforming or that unstructured data into a structured representation. So during feature extraction, you can think of different types of features depending on the application in hand, but generally we advise you to extract all possible kinds of features, right? Like, while introducing myself to you people, these two coordinators went on telling about myself, right? My bio, my background of education, where I have come from, what I am today, where I am working for, what are my social, responsibilities, etc. But all features that they have spoken out about myself may not be of relevant features to you people, because it is an academic sector. You don't mind whether I am providing really a good service to the society or not, but you look at what are my credentials as well as my research contributions are concerned, right? So probably that's what is called. So initially we just go for describing. I mean, extract all possible varieties of features from each sample of your interest, and then think of selectively choosing something of your interest. Selectively choosing some features which really appear to be rich in accomplishing your task, right? That's what is called dimensionality reduction. Yesterday, Professor Nagendra Swami was narrating a story of classification, telling us that, assume that there are n number of features. I mean, I have a vector of n dimension. So there are n characteristics, n attributes you would, n attributes, n characteristics. The fundamental question is that n really required? If that n is too large, should I have to go to work with such a large number of features, thousands of features? Can I reduce it? Then perhaps in the afternoon session, Dr. Shekhar highlighted that you can think of transforming that features n dimension to some other lower dimension, so that you will have less number of features but still representing the same data of my interest, right, without any loss of generality. That's what is called dimensional reduction, which is the topic of today's discussion, especially a specific kind of dimensional reduction technique called a feature selection. Once those features have been selected, or less number of features have been derived out of it, then we just inject into a learning model, and in parallel there are domain experts which are helping us in labeling these unknown samples for the purpose of training. And with the support of those domain experts, and these learning models will be created, and they will be reposited in the form of an index if the corpus happens to be so large. So we go for indexing to speed up the activities. And along with the images and the labels generated from the domain experts, we accommodate with a kind of annotations in the large corpus. That's what is called the outcome or a output of a training phase. I mean, this corpus, what you look at on the right side of the slide, is the knowledge base out of my learning. Once learning is done, we go with a relearning. Similar samples will be given, but domain experts do not get involved in this process of relabeling or recognition or retrieval. So we generally call it as a classification phase, and we pass through the same pre-processing. We prepare the data again with the similar approaches and extract the same features and subject it for dimension reduction. I mean, these are all the models which were learned and selected during training phase, and the same models are now executed, and we come out with a reduced feature vector. And this reduced feature vector will be given as an input to the classifier. Classifier could be a Bayesian classifier could be nearest neighbor classifier. That's what we discussed yesterday, right? And that classifier works with the corpus. The corpus gives the knowledge to that classifier. If the classifier job is to match this unknown vector, a reduced feature vector, which is given as input to it against already stored, right? Okay, the way in which it behaves, the style with which it behaves, the speed with which it behaves, the way in which it learns and attains the job, that decides what type of classifier it is. Is it a lazy classifier, or an active classifier, or a neighborhood based classifier, or a probability based, or a neural network? That's a different question. But now, given is a reduced feature vector. That reduced feature vector has got to be matched against what the vectors which were already learned yesterday during a training phase. And based on that matching, we just retrieve the top k based on the degree of matching. And probably when it is a problem of recognition, the rank one is considered to be the one or declared to be the ultimate. Otherwise, you can list them based on the priority. Look, dear friends, today's interest is on how well I can think of attaining this dimensionality reduction. So what are the different approaches available for dimension reduction in general, right? And where does this feature selection really suit? why that feature selection is so important today in spite of deep learning architectures, right? That's my fundamental question to be answered today. So dimension reduction in general, if I just say that any training phase create this two-dimensional matrix. Look, the rows in this matrix are nothing but the samples, I mean feature vectors. Column in this matrix are nothing but the features. Let there be n number of features extracted from m number of samples. Then we end up with m cross n matrix, right? This matrix is to use because m is very big, lakhs of samples I have, and n is also big, thousands in terms of thousands. I have 1,000 number of features. Then the question is, can I think of compressing it either in horizontally or vertically, right? I can think of reducing the matrix size. Either you can make m smaller, selectively choosing the samples as representative, or you can think of reducing the number of columns by selectively choosing the column or transforming all n columns to a different d columns where d is considerably less, right? Far less than the n value. So look at, if you compress this way, reducing that m to some c, where c is very far less than m, right? Independent of sample sequence, irrespective of the sample sequence, then I say it's a cluster approach, which you must have discussed in second day of your FDP. So that's what is called reducing this matrix, right? All in all, so that number of rows become less when compared to the original. On the other hand, yesterday Professor Shekhar has spoken about 2 hours, especially on PCA, which transform this n dimension to some lower dimension, right? Some lower dimension. So that's what is called reducing the number of columns. So that reduction are accomplishing some level of reduction in the number of columns in the pattern matrix or in the feature matrix is what is called dimensionality reduction. So the dimension reduction is nothing but crashing of n features to d features, where d is considerably less, very, very less when compared to n, far less than n. So what are the advantages? I need not explain you because Shekhar has narrated in an interesting way, in a beautiful way, the advantages of DR, right? I can just simply pass through it. So I can assure reduction in memory. The data analysis becomes simplified because I like to work with less number of features. A cluster analysis or classification, classifier design becomes much easier instead of working with, clustering of samples which are, described with n number of features, right? So you are working with only d number of features, very less when compared to that. Obviously, your cluster analysis works faster, right? Similarly, classifier design becomes simple. So if you can reduce it to 2 dimension, only 2 features, then visualization becomes really possible, right? So instead of visualizing your sample space, in feature space of dimension 10, if you can visualize the samples in a feature space of plane, a 2D, then perhaps visualization can be more effective. So all in all, we can think of time efficient classifier. These are all the advantages of a dimension reduction. But look at one end, we are telling that as the number of feature increases, the accuracy in classification, the effectiveness in accomplishing the task also increases. But unfortunately, as you continue increasing the number of features, because the newly added feature may confuse the classifier, right? Because the newly added features may be the features which describes not only the samples of class 1, but also the samples of class 2, right? Almost equally. In such cases, that addition of a new feature perhaps pushes the classifier into confusion, though that classifier will have some failure in classifying samples of different classes. In such cases, it is better not to add up some new features. I mean, of course, the accuracy of classification improves as the number of features increases, and after some time it starts deteriorating. At what time it deteriorates, that decides. I mean, you have to understand here, one is the difficulty in handling. The difficulty in handling any situation increases as the number of features increases. On the other hand, efficiency of a classifier also increases. Then you have to work in reverse and find out a crossover point, and that crossover point could be an interesting point to decide the number of features to be used. Anyway, what type of features, how many features to be is really confusing job. Nobody even today has any knowledge, so that there can be some analytical closed form, a mathematical way of expressing, finally automating the task of deciding how many features are really good. Only thing, you have to study the data that you have. You must have a strong knowledge on the application of your interest, and with the background of domain knowledge, perhaps you can be so good in deciding what should be the good number of features. Now, if I speak about dimension reduction methodologies, basically we have 2 categories. One is feature selection. Feature selection, name itself indicates selecting some of the available. I mean, selectively choosing few out of several. I mean, I have a set of 10 features. I'm not interested in all 10. I'm interested in only 4. Then which 4? I got to select. I mean, this feature selection results with a subset of the original. Hence, it is also called feature subsetting. On the other hand, I have 10 features. I don't want to selectively, choose some of them. Instead, I just work out a function which takes all these 10 as input and then convert this 10 into some other 5. Then I say a feature dimension is reduced, but after reduction, whatever the feature I will be working with, they are not original, they are the transformed. And such kind of dimension reduction techniques are called feature transformation. Yesterday you discussed principal component analysis, right? Principal component analysis transforms n-dimensional features into m-dimensional less number of features. So this is called feature reduction. So look at the complexity of feature selection, because I said is basically a feature subsetting. It is a process of choosing D out of n features. Then I'm looking for a subset of cardinality D selected out of n number of features. So how many possible subsets are there for that set with n features? 2 power n possible subsets, right? It's a power set of it. So even for a reasonably sized n, if n equals 10, I am talking about only 10 features, then the possible number of subsets is 2024, right? Sorry, 1024. Even for a reasonably sized n value n equals 10, the number of possible subsets rise up to 1000. Look at the complexity of that algorithm of generating all possible subsets and then verifying whether my classifier really performs wonder, for which subset it really performs better. I got to check with all possible subsets. I mean, I got to verify the performance of a system by running it 2 power n times. When n increases, this 2 power n exponentially grows, then it is practically not feasible, because it's an exponential time complexity problem. So practically it is indeed impossible to think of generating all possible subsets and then finding out the subset based on performance of the classifier while running it every time. Instead, we are looking for some approximation algorithm, some optimization algorithm where I can selectively search for the subset of my interest. My interest may be a subset of cardinality 4. I don't mind if I end up with a subset of cardinality 5, but I expect both the subsets to be almost same as far as the performance of the system is concerned. That is what is called feature selection approach. So on the other hand, if I look at the feature transformation, here is a space called original features. Here is a space called original features, and you have got to apply. For example, because you are familiar with PCA, a PCA could be the transformation. When you apply the PCA will transform into a new set of features. Basically, strictly speaking, and Dr. Shekhar also highlighted that issue, most of the times I don't canvas PCA as a dimension reduction, I just canvas PCA as a feature transformation technique. It just allows me to get myself replaced in a n-dimensional space. Instead of using this as a particular origin where I am standing and looking at all samples, but unfortunately from this point of view, when I look at all samples being here, probably I may not be able to see a couple of samples. Then I get myself adjusted, my position adjusted so that I stand at some other position so that all samples become visible for me for classification. Then I got to recompute the coordinates of all those samples with respect to this new position. And the recomputed values are nothing but the transformed features. Then basically, strictly speaking, as far as principles of PCA is concerned, the PCA transforms n-dimensional vector to n-dimensional only. But while transforming, PCA would also advise us of all n-dimensional features, which are of really great importance and which can be given a least important, so that it gets us the features in a sorted way, so that you can end up selecting only the first few and neglecting the remaining. That's why the PCA can be also exploited for the beauty of feature reduction. So original features transformed to some other new set of features. I mean, these new set of features are not the subset of the original available. They are completely computed out of this. Every feature computed is supposed to be a function of every original, right? But whereas in the case of feature selection, hope I am making clear that in the case of feature selection, I have 1, 2, 3, I end up selecting 2 of this, or I end up selecting 2 of this. But in the case of transformation, all these 3 will be simply thrown out, but new set of features will be computed as functions of these 3. This is the basic difference, the fundamental difference between the feature selection approaches and feature transformation based feature reduction. Look, here is an example for you. I mean, I have a feature matrix where there are n number of samples and 10 number of features. So what does this feature selection do? It converts this matrix of size 6 cross 10 to a matrix of size 6 cross 9, 3. So here feature 2, the column number 2 is selected. Feature number 5, column number 5 from this is selected. Feature number 9, column number 9 is selected. Only these 3 have been selected, assuming that these 3 would perform better. Look, when it's a question of pattern recognition, or when it is a question of classification, classifying samples belonging to different classes as member of its own class, then my interest is not to go with the features which are so rich in describing every sample, but my interest is to go for selectively choosing only those samples which are rich in discrimination, right? Hope you are understanding that. I am looking for a particular sample which is so good, which is so rich in keeping a sample of class 1 away from the samples of class 2. Similarly, I am looking for another feature which is so rich in keeping the samples of class 2 away from all the samples of class 1. Then those 2 features are good enough for bifurcating, for separating the samples of class 1 from that of samples of class 2, right? So this is what is the philosophy behind feature selection. In feature selection, I am in search of those features which are so good in separating samples of different classes, right? So that's what is called a subsetting method. Look at here, X basically is a sample chosen from, what is the space? Space is this, whereas in this neo, the space is reduced to only 3, right? Only 3. So look in this particular table, I have taken a 8 number of samples. Let's assume that there are 8 samples where each sample has been described by 3 features. So look at, if I go with only F1, please try to understand, if I go with only F1, then the value of F1 being 1 confuses me between S1, S3, because both the sample S1 and S2 bear the same value 1 with respect to F1, and F1 cannot be used to uniquely identify these samples. Similarly, F2 also, because F2 confuses me between S1 and S2 because both the samples have got the same value with respect to F2. And F3 also same, 6 and 6, 16 and 16. Look, if I go for F3 based classification, then I cannot distinguish S3 from S4. I cannot distinguish S1 from S2 and so on. Instead of that, if I go with all the 3, look at 1, 15, 6. This 1, 15, 6 triplet doesn't repeat here. Hence, S1 is unique with respect to all the 3. S2 is unique with respect to all the 3. S3 is unique with respect to all the 3. So then the question is, should I have to use all the 3, or can I selectively choose, if not one, right, a pair of features, so that these 8 samples are still distinguishable? Then the feature selection would recommend that, look at, why do you go with F2? F2 is not at all required just to differentiate these 8 samples. Then it says, go with F1 and F3. This pair, 1 and 6, will never repeat here. 1 and 16 will never repeat here. Though 1 repeats, but the second feature helps us in distinguishing them, right? Where though F3 repeats 6 and 6, but the first feature would help us in distinguishing those 2 samples. Look at, instead of working with these 3, F1, F2, F3, I can think of working with only these 2. There is no loss of classification, right? If the classification algorithm gives you 90% accuracy while working with these 3 features, the classification algorithm would continue working with the same accuracy even after reducing the number of features to 2. But look at here, this 1, 6, I mean a pair, is a subset of this triplet, and 8, 6 is a subset of this triplet, and all these is a subset of this entire, this matrix is a submatrix of this, and hence this feature selection is called feature subsetting. I'm looking for the best subset to accomplish the classification without loss of its accuracy or generality in general. On the other hand, the feature transformation here. Look at these 3 features. If you use F1, then these two bear the same. These two bear the same. If you use F2, these two bear the same. These two bear the same. If you use F3, these four bear the same value, right? Okay. Similar observation is true here also. Then if you use F1 and F2, then 1 and 5, 1 and 15, right? 1 and 15. Look, S5 also has 1 and 15. So then this pair is not possible. If 2 F3 pair, 15 and 6, 15 and 6, then this pair also will not help us. If you use F1 and F3, look at 1 and 6. Here is 1 and 6 again. I mean, neither F1 nor F2 nor F3. Neither the pair F1, F2, F2, F3 or F3, F1, right, would help in classifying these samples uniquely. I got to inevitably go for all three features. If I want 100% accuracy, if I want my classifier to work better, I got to inevitably go with all the three features. No subsetting would help me out. In such cases, I can think of recomputing some new values out of these three, right? Then what do? I generate these two columns. New features, F1, small f1. This is completely a function of these three. This 41 is computed out of three values, 1, 15, 6. How is this 41 computed? That's a different story. But this 41 is computed as a function of these three values. Similarly, 1458 F2 is also computed as a function of these three values. When these three values are given as input to this transformation T would end up giving me a pair of values, right? 41 and 1458. Similarly, when this triplet 8, 15, 6 is given as input to this transformation, then it ends up giving me 57 and 128. And similarly, all these triplets have been given as input to T got me a corresponding a pair. And when you look at this pair, each pair is different from the other pair. Now, instead of working with these three, features, what do? I just transform them into these two and continue working with these two features. Then I have accomplished a reduction in number of features from a triplet to a pair. I mean, basically, look at these three features are used as input to this transformation. The transformation function got me this F1 and F2. What is the transformation especially I applied here? Look at, this is the one with which you're all well familiar and studied in your school, quadratic solver. What is this quadratic solver? I just thought of assuming that these are the coefficients of a quadratic equation. Then I say it is x square plus 15x plus 6 equal to 0. It is 8x square plus 15x, plus 6 equal to 0. ax square plus bx plus c equal to 0. These are not assumed to be ABCs. When these are assumed to be ABC, these F1 and F2 are taken to be the roots of that quadratic equation. So roots can be computed as x equals minus b plus or minus square root of b square minus 4ac by 2a. When ABC, a triplet, is given as input to that function ends up calculating two roots, and these are the two roots, of course, scaled version of the roots multiplied by 100. Okay. Look at this quadratic solver can be used to convert a triplet into a pair, but these roots are the functions of these three values. So this quadratic solver works like a transformation function. Like, strictly speaking, this quadratic solver can be called as a dimension reduction technique because it doesn't transform you from a 3D to 3D. It takes you from 3D to straight 2D. Whereas in case of PCA, please remember, don't get confused. In case of PCA, you are moving from n-dimensional space to n-dimension only. But because you have got some knowledge on the way in which it transforms you and gets you the features sorted in order, you can selectively choose few out of several. But it doesn't strictly move you from n dimension to a lower dimension. Look at in this space. Again, let me go back and tell you, in this transformation, your input space could be of n dimension, output space could be of m dimension, n and m. If n and m are same, you continue to be in the same space. Same space, I mean a space of same dimension, but you get yourself relocated as a new origin. And with respect to that new origin, the coordinating systems, the coordinating values of those samples are recomputed. If m happens to be strictly smaller than n, then this T can be straight away called as dimensionality reduction technique. If M happens to be, sometimes we do this, M happens to be larger than N, I mean N can be 10, M can be 20, I'm moving from a lower dimensional space to higher dimensional, right? Then I say it is not a feature reduction, it is not a feature transformation, of course feature transformation, but not for reduction, it is a feature enhancement. It is not dimensionality reduction, it is a dimensionality enhancement. Sometimes we recommend you to go for enhancing the dimension for the purpose of subsequently reducing the dimension, right? I will come to that little later. So please understand here, this quadratic solver straight away takes you from a 3D to 2D, and such a kind of transformation is strictly considered to be classified to be a dimensionality reduction technique, okay? So if I go with the feature selection methods, basically we have a filter method and then a wrapper method, a combination of these two, one filter, one wrapper, combine them and see that both will work together for better performance of the system. Or you can think of, instead of combining filter with a wrapper, wrapper with a filter, you take two filters and combine them, or you take two wrapper methodologies, right, and combine them, and that's what is called ensembled method. So filter method is basically called as learning algorithm independent. I mean, I select the features without keeping in mind which classification technique will be employed for my task. Whether I work with nearest neighbor, or I work with decision tree based, or I work with SVM, it doesn't matter. I don't look at it at all. I just look at the features, I do feature engineering, I end up selectively choosing couple of them, independent of learning algorithm, right? And that is what is called a filter method. So here, while selecting the features, I got to evaluate each feature. For the purpose of evaluating each feature, I got to think of some criterion, right? And I mean, take a feature by feature one at a time, subject that feature for evaluation, compute some score, and based on the scores that you obtain for all features, decide which features are really good for you. It's exactly like selecting students for master's education. The students have completed their bachelor's degree and they apply for master's education. I have only 20 seats, but number of applicants are 100. Number of applicants, there are 100 applicants, no, who is interested, who are interested in taking up admission for master's degree. Then how do I selectively choose only 20? Then I rank them, I take the average score in their qualifying examination, or if necessary, I conduct the entrance examination. I take up the entrance score, I just normalize and then produce a rank list. Then I go with the top 20. I mean, somehow I should find a method of sorting of features based on their degree of discrimination, based on their ability to discriminate samples. And such a feature, selection criterion has got to be worked out. And based on that selection criterion, I got to rank the features. Once features have been ranked, then I go for selecting the top K of my interest, top 10 of my interest, and such a method which works independent of learning algorithm is what is called filter method. On the other hand, why I'm selecting? If I know in advance, I'm selecting for nearest neighbor classifier. I'm selecting features for SVM classifier because SVM has a different behavior when compared to nearest neighbor, and Bayesian classifier has got a different behavior when compared to SVM. The features which got selected for SVM may not be the good features for a Bayesian classifier. The features which got selected for Bayesian classifier may not be the good features for some other classifier. Then if I have got some knowledge on well in advance what classification techniques I would be employing, if I stick on to that, why can't I think of making use of that knowledge as an added knowledge for ranking of features and then selectively choosing them? And such a feature is what is called wrapper. It wraps around a learning algorithm. Wrapper technique is purely dependent on learning algorithm. And performance criterion is required here. It's not a feature selection criterion. Here I got to work with the performance criterion of a classifier. Maybe accuracy, maybe F feature, maybe precision of that, maybe recall of it, or F measure of it, or it could be R norm of it. Any validity measure you have to decide, associate with the classifier, and every time when you select the subset, run the classifier and check with the performance of the classifier and choose the subset of the features which leads, which drives the classification model to perform maximum. And that technique is what is called wrapper technique. For example, see, in a national institute like IITs, national institutes, still our universities and colleges have not reached to that level. In national institutes like IIT, IIIT perhaps, there could be two teachers who are ready to offer a course on, let's say, data structures. I mean, the teacher T1, teacher T2, both are ready to offer course on data structure. Any students can enroll for any of these teachers, but the number of students who can, the number of students to be selected for each teacher is only 10. But interestingly, when you look at the background of teacher 1, he appears to be a teacher who loves data structure course, but unfortunately not with a strong background of mathematics. I mean, he teaches well data structure, but unfortunately, he doesn't represent data structure from the background of mathematics at all. He never thinks that set theory is useful, but he just narrates the story of data structure as if he is narrating a story. Whereas on the other hand, teacher 2 always, whenever he goes on dealing with any data structural aspect, he always brings in mathematics. He enjoys bringing in mathematics. Then the question is to select 10 for the teacher 1, 10 students for the teacher 2. While selecting a student for teacher 1, I prefer those students who are not that necessarily good at mathematics. Or I prefer the students who don't necessarily like mathematics. But whereas in the case of teacher 2, I have got to select only those students who love mathematics, right? Otherwise, they really find it very difficult to attend through his lecture. Look at, if there is a teacher, and with respect to the teacher, if I drive my method of selecting students depending on the teacher, then I say it is a wrapper technique, right? On the other hand, I don't look at the abilities of teacher. I just 10 students have got to be selected. How many students have applied? You just rank them, choose the top 10, assign with the teacher. That's what is called a filter. Then you must have understood that the method of selecting feature subset, keeping in mind knowledge of the classification algorithm, perhaps works better, Yes, obviously, in the literature, wrapper techniques have been demonstrated to be performing better than a filtering method for selecting, but unfortunately, while selecting a subset of features, we have to run classification algorithm every time, and it leads to a time complexity. I mean, for a large collection, when we talk about big data, when we think of scalability of the problem, then wrapper technique doesn't suit in practicality. The filter techniques, being independent of learning algorithm, would suit the reality. So nowadays, we the researchers concentrating more on filter method rather than wrapper method, right? So this is the fundamental difference between filter technique and a wrapping technique. Another example could be, look at, there is an international cricket game. There is an international cricket, match which is planned to be held in the month of December of this year. Then the Indian cricket team has got to be selected. While selecting 11 players of cricket, what do? I just choose 11 players who are the top performers of India, right? Amongst all Indian cricketers, I just choose the top 11 performers and make a team. Whether it's a good team or a bad team, I just make a team. This is one way of selection. On the other hand, I just look at, in the month of December, how many other countries are really participating. Then I come to know that there are only two countries. One is from Pakistan, another one is from Sri Lanka. I mean, only 3 teams are involved. The other 2 teams are from Pakistan and Sri Lanka. I know the players of Sri Lanka and Pakistan, right? If I can choose 11 players of India who are great performer against, Pakistan and Sri Lanka, that turns out to be a better team, right? Look at selecting team members, keeping aside the opponent teams, and or selecting team members, considering the opponent team, right? Both are entirely different. The end result should be different. But selecting team members, keeping in mind the performance of the opponent player, perhaps works better in building up a team. Similarly here, in feature selection, wrapper techniques works wonderfully well when compared to any filter method. But unfortunately, nowadays, because most of the applications involve large collection, right? Large corpus, wrapper technique is time inefficient. That doesn't suit the practicality. That's why we are talking about hybrid model. What do I do? Instead of going with a large dimension and running the classification algorithm many times for wrapping method, why can't I think of applying filter first, reduce the dimension from lakhs to 100, and then apply the wrapper, so that wrapper becomes practically possible, right? So this is a fundamental differences between what is called filter and a wrapper. Hope I made it very clear. So if I now get into the filter design, basically it has two steps. As I already narrated, one is to rank the features. I mean, if there are n number of features, every feature has got to be subjected for evaluation. Once feature is subjected for evaluation, I end up computing a score, and I do it for all n. And based on that score, I just sort the features according to the relevance. I mean, the first fundamental step is end up selecting relevant features, right? How many are top after sorting? After sorting, you select 10 features, for example. But when you select the 10 features, the first two features, though are the top features, but maybe redundant features, who knows? They are one and the same. Because they are one and the same, they are ranked to be the first and second. So then you have to eliminate such redundant features after selection, right? So that's why a filter is basically two-step process. One is a selection of relevant features, and the other one is subsequently eliminating redundant features. For example, I select 11 players for Indian team. Looking at their top performance, looking at their, what do you call it as international rankings. Based on the international ranking, if I just end up selecting 11 players, probably my Indian team may have only batsmen top 11. I mean, the Indian team will have all 11 players who are batsmen. That's not a good thing, right? When you select one batsman, perhaps selecting the next batsman appears to be redundant, Then I want another person who is a good bowler to be added into the team, right? Then I think of eliminating 5 batsmen who appear to be redundant when compared to the other batsmen, and bringing in the bowlers, though the bowlers are internationally at low rank when compared to this batsman. This is what is called the necessity of eliminating redundant features. Look, basically, a filter design involves two steps. One is selecting relevant features, and then amongst selected relevant features, reducing or eliminating redundant features. For example, for the purpose of selecting relevant features, I have to go for some dispersion measure. Here are the n number of features. Look at the slide. Here are the n number of features. Then what do? For this feature 1, I compute some score. Compute the score. The score can be how much is the variation this F1 preserves across all samples of the population, right? How much is the variation that F2 preserves across all samples of the population? Yesterday, Dr. Shekhar was talking about if the variance is mean variance is 0, right? That's one concept. Another one is if there is no variation at all, if zero variance. If there is a zero variance, then all values across the samples are one and the same. In such cases, this feature has no relevance. Then assign with a score very negligible, very small. I mean, the first step is compute the score. For the purpose of computing the score, you have got to think of a criterion called feature selection criterion. It could be many. That's what I call it as a dispersion measure. Any dispersion measure for that matter. So use that and compute the score. Once scores have been computed, let's assume that V1 is a score computed for F1, V2 is a score computed for F2, etc. Vn is a score computed for Fn. Once these scores have been computed, then what do? I sort these features, sort the features F1, F2, etc. Fn based on these scores. Whatever which has got, suppose F4 is the highest among all these, then bring in F4 first. If V2 is the lowest, I mean the smallest among all n scores, then keep this F2 at the end. Just sort the features, right? Like Fi comes first, Fj comes next, Fk comes next, Fp comes next, etc. Fl goes at the last. So once these features have been sorted, how many features you want? Let's assume that m features I am interested in, where m is smaller than n, and choose those m features from the beginning, right? Choose those m features from the beginning. Look at, in case of feature transformation like PCA, for example, these n features will be converted into another n features. But while giving these features, listing out these features based on the eigenvalue, PCA would get you them sorted. Then choose the top m, right? To choose the top m. Now, among these m, some of them may be redundant, right? So how do I compute this scores? Use some dispersion. The dispersion measure could be mean absolute difference. What is this mean absolute difference? Look at this feature F1 has got n, has got values across samples. Let there be m number of samples. Then there are m values, right? Take the mean of that, right? Mean of that, and subtract every feature value from the mean. Every feature value from the mean. Take the absolute value. Compute the mean of that absolute difference. If that mean of the absolute difference is high, obviously there is a variation across samples of the population. Then you can use this mean absolute difference as one of the criterion to select the feature. So for whatever the feature where mean absolute difference is high, that could be listed first. Whatever the feature where the mean absolute difference of that feature is very small when compared to all other, that could be listed out at the end in the sequence. And once sequence is produced, you just take top m, right? That's what is one criterion. The other criterion could be variance, right? You compute the variance of a feature, variance of the next feature, and whatever the feature which has got the highest variance will come first in the list, right? Then we have arithmetic geometric mean. I mean, take the arithmetic mean, add up all values of that feature across all samples of the population, that and then divide it by the number of samples. That is arithmetic. Multiply all values that feature has across all samples of the population, right? And take that root, nth root if there are n values. That's called geometric mean, right? And take this ratio of that. If the ratio is high, the feature is said to be highly discriminable. If the ratio is less, the feature is said to be of less discriminable, right? You can use this arithmetic and geometric mean also as one of the criterion. Or you can use mean median difference. Mean median difference means compute the mean of this feature and compute the median of this feature. If that mean median deviation is high, the feature is said to have high discrimination ability. If that mean median are one and the same, then that variation within the samples of the population is negligibly small. That doesn't suit your purpose of identifying uniquely the features which is capable of establishing high discrimination. So you can use mean median difference as criterion. You can use Fisher ratio. It's for supervised learning. I mean, look, these are all unsupervised learning. I don't use any knowledge on the class labels of the samples. Whereas in case of Fisher ratio, I use the labels of the class sample, right? So class labels will also be made use of Fisher ratio, right? So that's for supervised environment. Once these M features have been eliminated, have been selected, then you check whether F1 is correlated to Fj. If Fj is correlated to Fm, right? If Fi and Fj are one and the same, right? One and the same. When I look at the values of Fi across all samples, and when I look at the values of Fj across all samples, if not one and the same, look, if it is 10, it could be 100. If it is 20, it is 200. If it is 30, it is 300, right? Then it is just multiplied by 10. If Fj can be expressed as a function of Fi, then why do you want this Fj, right? Because that becomes a redundant. If one is expressible in terms of other, if one is dependent on the other, right? Then you can think of eliminating, and such features are called redundant features. Suppose I make a committee of 5 members, right? In a university or in a college, there is a committee to make some decision. I make a committee of 5 members, but there is one person called a leader, right? A captain of that. Then there are 4 members. Among these 4 members, look at, if the 5th one always says yes when the captain says yes. If 5th one always says no when the captain says no, I mean the 5th one goes with the decision of the captain, then do you think that the 5th one is really required as a member of the committee? No. And such a person is what is called a redundant person. In the committee, everybody has to have some discussion, before coming with some agreement. So that is individuality. As long as the features are individual and they are different from the others, we can retain. If you find something which is highly correlated with the other, remove one of them so that M can further be reduced to some D features where D is very, very small when compared to N. This elimination is done with the support of similarity measure. How similar the feature 1 with feature 2, how similar feature 2 and feature 3, how similar feature 3 and feature 1, right? If you find any two of them most similar, you eliminate one of them and keep the other one so that you can further reduce it. And this 2 steps is what is called a filter design. For the purpose of establishing a similarity, you can either go with the cosine similarity function or you can go for computing the correlation coefficient, any similarity measure for that matter. I mean, basically what you are going to understand is you can think of your own filter method for your own application. It's not necessary that you are going to make use of the standard, benchmark, the criterion which are available in the literature. Look at the data, look at the samples of your interest, understand the purpose of classification, and keeping that, you can think of your own filter, a new way of filtering of the features. Filters, as I said, is like a coffee filter. When you pour the coffee, the filter does what? It attenuates unwanted and allows only wanted. Similarly here, the filter takes all N features, allows only wanted features to pass through by blocking unwanted feature, right? Why can't you think of your own filter strategy? But when you attempt to design your own filter strategy as output of your research contribution, then you have to think. Basically, filter has 2 steps. One is selecting relevant feature. The selecting relevant features involves exploiting one of the feature evaluation criterion. That evaluation criterion could be your own new one, right? And subsequently eliminating redundant features. How do I check whether the feature is redundant with respect to others? You can think of your own criterion. If these 2 criterion happen to be new, then you can canvas that I come up with the new filters, right? And which works better for my application, right? So that's what you can you can think of coming out with your own filter design for application in hand. So you can also do, and this has been explored well. Instead of going with these 2 steps, you can follow in a different way. Anyway, I have N number of features, right? And on the second day, if I remember, somebody, some resource person, had given a lengthy explanation on data clustering. What do you mean by data clustering? Data clustering is nothing but identifying the internal relationship existing among the data. I mean, whatever the data which exhibit high degree of similarity are placed in one group. Whatever the data which possess less degree of similarity, I mean high degree of dissimilarity, will be kept in different clusters, right? Similarly, I have N number of features. Assume feature itself is a samples for me. Feature itself is a data for me. Then can I study how these features are related mutually? Then do a feature engineering. Instead of clustering the data sample, you cluster the features. When you cluster the features, you end up with some number of clusters. From each group of features, from each cluster of features, why can't you think of selectively choosing a representative, right? That could be a wonderful, filter concept today. So clustering of features and then choosing cluster representative. For example, see here, I have a objects versus features. This is how conventionally in machine learning, we represent every pattern in terms of features, right? This is the data matrix. The data matrix has got to be transposed so that you will have each row a feature. Here each column is a feature. Now each row becomes a feature and each column is an object now. Instead of clustering object, I go for clustering of features. When I do clustering of features, either you can think of any agglomerative strategy or any partitional cluster. If you are, having some knowledge well in advance, how many features you are really interested in, right? I have 100 features, but I have got to work with only 7 features. If you are very particular about number of features to be selected, right, then you can go with any partitional, k-means, fuzzy k-means, any partition clustering. But partition clustering requires an added knowledge on how many partitions you want. Either you can use agglomerative or you can use partitional. In that case, I want to generate D clusters. Then what does it do? It gets me the D clusters. Look, feature 3, feature 4, feature 21 are put together because they exhibit high degree of similarity. Whereas feature 31 and feature 14 are put together as members of the same cluster. Why? Because they possess high degree of similarity. But on the other hand, F3 and F31 have been placed differently because they exhibit high degree of dissimilarity or less degree of similarity, right? So The clusters have been obtained. Now, once clusters have been obtained, from each cluster, you choose a representative among these 4, which is the best one. Among these 3, which is the best one? Among these 2, which is the best one? There are many. Oh, which is the best? I mean, choose one among several, right? One cluster representative. The choosing cluster representative could itself be an interesting topic, right? Then what do you have to do? You have to establish a similarity and think of a graph representation and choose the center of the graph, right? That could be the best one. Choose the center of the graph. That could be the best one. Choose that. Right? So if you end up selecting only one, which is all available here, like F1, from here F14, from here F21 I select. Then I end up selecting F4 from this group, F8 from this group, and F31 from this group, and some are from this group. Then I selected one thing. Another thing is, because these are all placed to be together as members of the same cluster, why can't I think of averaging of all the features, right? Look, I don't select F8, nor even F1, nor even F2. None of these get selected. Instead, something is computed out of these 4. A new feature. I take the average of all the features, right? Mean of all the features, and that newly computed one will be selected as representative. In that case, I don't say it is a feature selection. I say it is a feature transformation, right? It is a feature reduction, not through subsetting, but through transformation. For the purpose of transformation, I go for grouping of likelihood features, right? Similar features, and then average them, or I just compute something. That's what is called a transformation. If this selecting representative happens to be strictly one of these, then it is strictly feature subsetting, feature selection. Otherwise, it is called feature transformation. So you can think of this way of selecting features also. On the other hand, wrapper method. As I told you already, wrapper method is a method which wraps around the classification algorithm. You must have a knowledge and you have got to stick on to that. I am selecting these features to drive this classification algorithm. I mean, the selection is totally dependent on the subsequent learning algorithm, SVM. I end up selecting F1, F2, F3. If it is nearest neighbor, I may not end up selecting the same F1, F2, F3. It could be F5, F6, F7, right? Because every classifier has got its own behavior, and based on its performance, based on its behavior, I end up selecting different subsets. So here wrapper methods are purely dependent on, right, classification algorithm, learning algorithm. So basically we have two. One is sequential forward, the one which starts with a empty set and goes on constructing a subset of interest by adding up the features each stage. Whereas sequential backward selection, it starts with all the features and it goes for eliminating the feature. These are the two ways, right? I have 10 values. I got to end up selecting 3 values. One is selectively choose 3 and construct the subset of 3 values. Or amongst them, you go on throwing out one by one, 7 times, you end up with the 3 values, right? That's what is called. One is a sequential forward, the other one is a sequential backward selection. Combination of this called ensemble. I mean, you can think of combining sequential forward with sequential backward, or you can think of combining sequential backward followed by sequential forward. So those are respectively called sequential floating forward selection, sequential floating backward selection. Those are generally called ensemble methods. If I just speak about sequential forward selection, look, it is a method of inclusion. It goes with the method of inclusion. I mean, it starts with an empty set. Initially, I have 5 features, right? Still, I am working with 5 features. Initially, the number of features selected is empty. Then what do? I have a classifier C. I decided SVM is my classifier. Then what do? I take only feature 1 first. Evaluate the performance of classifier SVM. What is the performance? 71%. F2, 68%. When I run the SVM with respect to F3, it is 55%. When I run the SVM with respect to only F4 feature, considering only F4 feature, then its accuracy is 43. When I run SVM with respect to F5, its accuracy is 49. But when I have executed SVM for classification by using feature F1, then it had 72%. Then which feature is working better when compared to other? F1. Then what do? From these 5 features, I end up selecting first F1. Now the features left out are these 4. Then what do? Which one can be added into this? Then I try F1, F2. evaluate the performance of the system. F3, F1, evaluate the performance of the system. F4, you add up F4, then take out F4, add up F5. Then you try with the pair, F1, F2, F1, F3, F1, F4, F1. Look at the complexity of wrapping technique now, right? Indirectly, if not all possible to power in subset, at least some of them got generated, right? And each time when you evaluate it, 4 times you have executed here, and F4 appears to be a better feature to add up, then add up F4. Then go with the next. And each time, whether it ends up with improving. Earlier it was 72 when F1 alone is used. When F4 is added up, now the best performance is 78. Yes, improved. Go with that. When the another, again, you try adding F2, the triplet, adding F3, making another triplet, adding F5, making another triplet, and check the performance. The performance is now has become 88. Oh, now better. To add up the new one, that's called F5. Now the feature selected or F1, F4, F5. Now I got to check with whether addition of F2 still improves or addition of F3 still improves or not. When I just checked with addition, of F2 and also addition of F3, perhaps that 88, has come down to 63 when F2 is added up. When 88, when F3 is added up, 88 has come down to 82. Then however I try, it's not at all possible for me to improve the performance of the SVM classifier. Then it's better to stop with F1, F4, F5. So look, it starts with the empty set and goes with a method of inclusion. It always adds up a best feature such that the performance of a learning algorithm is maximized and stops when we cannot further continue. And that way of selection of features, constructing a subset, is what is called sequential forward selection. Notice here, you are not trying to generate all possible pairs. Here, you just have generated only 4 pairs where F1 is mandatorily used. But we never have checked, we never have come across with any circumstance where I have verified the performance of the system by considering F2 and F3, right? F2 and F3 pair must have been the most performing, wonderful pair. But unfortunately, because F1 got selected in the beginning, F1 when alone, considered, appear to be performing better. But F2 when alone is considered, appear to be performing less. But when F2 is used along with F3, perhaps the F2 works much better. But we did not have any such situation where we just have trained our model and verified the performance with a subset called F2 and F3. Look, though it appears to be a model which generates possible subsets and verifying the performance of the system to select the best subset, but it doesn't generate all 2 power n subsets, only a subset of 2 power n subsets, right? Okay, so the which feature gets selected first, that matters a lot, right? Which feature gets selected first, that matters a lot in deciding the quality of the subset that you generated. That you have to keep in mind. So in case of backward selection, it works in reverse, a method of elimination. It starts with all features, all n features, right? And then go on eliminating the low performer, right? Low performer. I have got 20 members, but I got to end up selecting only 11. Then find out who is a low performer, worst among all. Then eliminate. Next verse, eliminate. Next verse, eliminate. Continue doing, right? So starts with empty, which is right, nothing is eliminated, then F3 is eliminated, and then F5 is eliminated, and so on. And then finally you end up with F2, F4. This works in reverse. Look, these 2 phenomena or strategies called selection, forward selection, sequential forward and sequential backward, though appear to be reverse in nature, they are not duals. 2 processes, P and Q, are said to be dual. If one works in the reverse of the other, still end results are same. But here, the sequential forward selection and sequential backward selection, though appear to be reversible each other, but strictly end results are not necessarily same for all applications. Hence, don't take them as dual strategies. So instead of going with only filter or only wrapper, you can think of hybridizing, right? As I said in my explanation earlier, you take the training data set, apply the filter method, reduce the dimension to a lower dimension, and then go with a wrapper, because wrapper suits better when the dimension of the space is reasonably less. Then apply the filter in case if you are working with very, very high dimensional space, apply the filter strategy, reduce the dimension to 100 and go with a wrapper, and then do the classification. So that's hybrid. Ensemble is take set of original features. Why you want to try with only one criterion for feature ranking? Use variance, use arithmetic geometric mean ratio, use what Fisher criteria in case of supervised, and think of generating the ranks, 3 types, and then combine the ranks into single rank and then reduce the data set, right? That's what is called exhaustive search. You can think of combining multiple criteria and together into single criterion, either with and conjunction or with or conjunction and so on. I want to select the one, a feature which is either ranked first or either ranked here or either ranked here as first ranking, right? Wherever it comes as first, that goes first. Or you take the rank number here for a particular feature, rank number here, it could be third one here, it could be second one here, it could be seventh one here, add up all the rank, divide by 3, that gives the average rank. Based on the average rank, resequence the features and select the top EM, right? So that's method of combining, the same kind, filter to filter, wrapper to wrapper is what is called ensemble method. So sequential forward, look, it's a method of inclusion and elimination. I mean, ensemble method, sequential floating forward, whereas sequential floating backward. These are ensembled methods. Method of inclusion followed by elimination, whereas this one is a method of elimination followed by inclusion. It starts with empty set, whereas this starts with all features. So forward selection followed by backward elimination, whereas here backward elimination followed by forward selection. It is SFS plus SBS at each step, whereas it applies first SBS and then SFS. That's how, I mean, A comes first, then B, or use B first and then A. This is what is called method of ensembling wrapper technique. And basically we have only 2 types of wrapper technique. One is floating forward, another one is floating backward, right? So here is some, one example for you to understand how well the feature selection really help us. This is a old, results I'm putting perhaps 6-7 years back, what we have worked on medical images. This is a classification problem where there are about 5 classes. Look, class 1 to class 5, and the features were color, texture, and RGB histogram we have taken up. Totally computed 4,182. I'm just showing you as an example. Okay, extraction from our earlier work. So global features were computed, and number of samples for each class not necessarily balanced, imbalanced data class. So total number of samples used is 510. These are some example pictures of each class. Okay, how many features? Remember that it is 4,182. When the classification accuracy, precision, and recall and F measure were computed using all features, right, for a particular classification algorithm, these are the values, right? These are the values. When we have gone with feature selection method, MED, mean absolute difference, mean median difference, AMGM, arithmetic mean, geometric mean ratio, right? And this is the total variance. Look at the number which is put inside the bracket is the dimension selected. So instead of working with 4,182, the MAD technique has recommended only 3 features. Look at only 3 features, right? Only 3 features. Using those 3 features, this is the accuracy, this is the precision, this is recall, this is F measure. Similarly, using 3 features selected by method, this AMGM has given us 8. That appears to be performing better than all. Look, with a dimension of 8, with a dimension of 3. So here are these. When compared to this, original result, here is this. Okay. So with 8 feature selection, 8 features. I mean, what it quoted here is AMGM. So when original results are compared with the results obtained by AMGM, this is an improvement, right? Okay, as an improvement in each accuracy, precision, recall, F measure. So how many features we have used after selection? 8. Dimensional is reduced from 4,182 to 8. Look at the reductions, percentage, like very high, 99% almost, right? So that's the advantage of going with the feature selection technique. Another example is this. Due to COVID-19, so we deployed a wonderfully well face recognition system for thousands of subjects, people working in some organization outside India as a part of industry, assignment. And the system was trained on, faces without masks. I mean, the system was deployed in the month of December 19 and January 2020. There was nothing like COVID-19 situation. The people have enrolled without any mask. So we have used deep learning architecture to select, to generate features. The number of features generated were 128 in number, right? This is what example of a face image enrolled for recognition. The system was working wonderfully well, 100% result for thousands of people. But due to COVID, the people started coming with masks to the organization. Now the system, will stop working fine. I mean, because the people are not ready to remove the mask. But when the face with mask is given, the people, the system used to fail in recognizing. Then the task is to make the system so capable of recognizing people looking at only this visible area of the face. Look at these 128 features have been extracted by considering entire face. Now, some features have got to be extracted only looking at this visible area. Then the question is, which are all the features out of 128 which are the representative of only this visible area? That's a subsetting problem, right? Okay. So let me not explain in detail. Then we did some subsetting, way of doing it. Look at, here are some examples: a face without mask and face with mask, right? So the person enrolled with this face, but started coming with this. Then still, I expect the system to recognize, right? Okay, a person enrolled with this face, but earlier the system used to work even with a person enrolled without spectacle and without beard. But when person comes with spectacle and with beard, but now the person comes with a mask. How to make it? Then I get to selectively choose only those features which are representative of this area. But unfortunately, when the system is trained with the deep architecture, then subsetting is really a tough job. Then we just have tried it. Perhaps on Saturday I will present in a detailed way. So we just have gone with 128 features. Then the performance of the system when all 128 features are used is only 81%. Right? 19% were the failures. Earlier the system was working with 100%, but now 19% is the error. So mean difference, mean variance, these are the criterion used. 4 criterion, right? Look. Okay, number of features selected, not 128. Instead of 128, 90 features, 122 features, 75 features, 63 features, and so on. So then the accuracy, instead of 81.5, risen up to 90 point something, 84, 90, 89. Look at, there is always an increment irrespective of the criteria. Then what we have done, we just thought of going with a fusion, ensembled of features, filtering strategies, right? These 4 have been fused together to generate a re-ranking of the features. And when we are done with that, instead of going with 90 or 128 or 122 or 75, we just have thought of 74 top features, right? Which has given us an accuracy of 92.48. There is a considerable improvement, right? Earlier, the system used to work with 19% error. Now the system works with only 8% error, right? So feature selection. This is another example which recently we worked on, in a real-time application I'm talking about. Then the system deployed in a real-time application, and there were about 9 individuals who used to come to the office on alternate days, right? Because of COVID situation, all employees were not allowed to get into the office, only 9 at a time. So those, when we have verified the performance of the system, only for 9 people, instead of considering all 1,000, thank God that the system started working with 100% every day for the 9 subsets selected, right? So this is quite interesting, application we handled and made it possible in real-time application, our AI, right? So further, in our lab called DAL, Data Analytics and Learning Lab of Computer Science Department of University of Mysore, we have been pursuing, machine learning problems on various applications. And as a part of, a piece of the research work, in almost all applications, we canvas towards feature selection. Look, dear friends, basically subsetting and transformation. Generally, when the data set happens to be large, transformations are not practically usable. Then feature selection. Under feature selection, we have subsetting and wrapper. When the dimension of the feature is too high, wrapper doesn't suit, only subsetting. When the subsetting is so only filter. When the filter is used, then you can think of possibly many filters and fusing them together for effective way of selecting the subset of your interest. And then still you want to select the features relevant to a classification algorithm of your interest. If you are so particular about the classification algorithm, then I would recommend you to go with hybrid technique instead of an ensemble technique. Hybridize a wrapper subsequent to a filter. Apply the filter, reduce the dimension, and then go for wrapping technique by fixing up your classification algorithm. So we have been pursuing, these are all the list of publications. Recently, we just have come out with one, publication in pattern recognition letters elsewhere journal, where we have recommended an alternative framework, especially for a supervised learning, feature subset selection for supervised learning, class dependent, then instead of generalizing the evaluation of a feature, why can't you study the feature with respect to a class? Then if there are k number of classes, for a particular class 1, try to find the best feature which is capable of keeping all samples of class 1 away from rest of the samples, right? Rest of the classes. Then select another feature, feature number 2, which is capable of discriminating not class 1, class 2 samples from all other samples. Then if there are k classes, you end up selecting only k features. So that is an alternative framework which we have selected for supervised learning. So this you can read. I'm sure it will motivate you to think in your own way of, or in your own method of selectively choosing the features. So we worked on even interval valued feature selection. You can see, and we got pattern action letters, another expert systems application elsewhere, yet another for online signature, rater dependent feature selection, and so on. I wish you just Google it in my name or in my laboratory name. I'm sure you'll get a list of papers published in reputed journals. Just read through. At least you will have some kind of inspiration, motivation, so that you also can think of, instead of adapting existing, you can also think of your own method of feature selection suiting your requirement. With this, if I sum up my lecture, hope I'm on right time. Yes. If I sum up my lecture, I started with notions of dimensional reduction, a general way of understanding it, and then discussed on filter methods, wrapper methods, specifically into feature selection, and hybridization of these two, ensembling of any one of these with multiple instances, and quoted 2 examples, basically one on medical image, skin image analysis, another one into face recognition applications. Friends, one thing you have to remember, sir, is it always possible to think of extracting or finding out such features which are so rich in discriminating samples? Is there any guarantee? Then I'm sure I would rather say, in my own philosophical way, look, there is always a distance. There is always a distance between 2 living things. Even in twins, there is a distance. There is some discrimination. At least mother identifies it, right? I may not be able to distinguish 2 twins, but mother does it. Look, there is always a distance between 2 living things, as it is unlikely that any 2 living beings are alike. No 2 can be alike. Otherwise, they are called single, right? As long as you say they are different, as long as you say they are 2, there must be something which distinguishes them. It is even true with artificially made objects, however they are visually alike. With this message, I'm sure you can boost up your confidence, think of selectively choosing or searching for. But what is very important is, look, the mother searches for such a feature which is capable of distinguishing 2 kids which are twins, right? And that method of searching is supposed to be more effective and efficient. Look for that and go with that. With this, if I terminate, then perhaps my lecture appears to be incomplete. I get to extend my heartfelt acknowledgement specifically to the organizers, with a special thanks to Madam Sharmila for having given me an invitation to share my views on feature selection approaches, right? And I must also thank my research scholars, especially past and current, who have given me a rich experience to put the things in my own philosophical way. And more so important, my mentor, Professor Nagbhushan, who has boosted up confidence in me when I was doing my PhD work. With this, I thank you one and all. Thank you very much.
Thank you for such a wonderful session, sir. It was really superb session. The way the quadratic equation was linked to feature selection, I am sure it have had triggered the minds of participants to think in various diversities. With that simplified and the crystal clear explanation on various feature selection approaches, I no doubt admit you are rightly called guru in the research community, sir. Thank you once again, sir. Now we come to the question and answer session. So participants, I request if you have any questions, kindly raise your hands. After your hands are lowered, you can unmute and ask the questions. So first question to you, sir.
Yes, sure.
How feature selection is done when neural networks are used for classification technique?
Correct. So not only that, this is what I have used, deep learning architecture, no? So deep learning architecture gives some number of features. So feature extraction that I will now present on Saturday morning, right? So while exploring possible avenues for researchers to dig out in machine learning. So when neural network is used for classification purpose, assume that the neural network is working fine 89% or working fine 100% for n number of features. Then the input neurons are n in number, right? There are n values getting injected into the neural system. Then you can think of another neural network which work with less number of features, giving the same accuracy, right? Then obviously you have to go for selectively choosing the features. So even under neural network also, we do the feature selection. So that's what I presented here in first face recognition applications. Though the system was built completely on deep learning architecture, not only classification, even feature extraction was also through neural network. But in between, we just have tapped the features and went on engineering, right? And then understood that instead of 128, it's good enough to use only 74. How did we do that? What are the alternative models? Perhaps I will touch upon that issue when I explore further avenues on Saturday lecture at 9:30, please.
Thank you, sir. It was an excellent session on feature selection approaches. I'm sure our participants have got several valuable inputs that will help them in their research work. You have clearly explained the various approaches of feature selection that is primarily required for any research work. We will be eagerly waiting for your next session, sir, on the 29th. Thank you very much, sir.
Sure.
So, dear participants, Dr. D.S. Guru sir will be joining us back on Saturday 29th with the topic research avenues in machine learning. I thank you again, sir, for today's session. It was
Thank you very much.